Okay, so we are now covering the second half of chapter 3, starting with Newton's laws, having just finished talking about Newton or Kepler's laws of motion, specifically planetary motion. Newton's laws are more general, at least Newton's laws of motion. I'm going to quickly run through Newton's 3 laws of motion. The reason I'm going to do it quickly is because they are not crucial to our understanding of astronomy. They would show up more in a typical physics problem. Now, to place Newton on our timeline, let's quickly review where we were. We've been talking about scientists and philosophers from 1473 up to 1642. When we introduced Tycho Brahe and Johannes Kepler, they were contemporaries to Galileo. So, in other words, they lived at the same time, which would have been the late 16th century, also known as the late 1500s, into the early 17th century or the early 1600s. Nicholas Copernicus was dead for any of them, living, practically a whole generation for, okay, more than a generation. But anyway, what we're going to do now is continue the timeline past the death of Galileo in 1642. The first time that we moved further forward in time. And after this, we're going to introduce Isaac Newton, who was born the year that Galileo died. He was born in 1642, and he lived until 1746. So he lived in the second half of the 17th century and died during the early portion of the 18th century. What is Isaac Newton famous for? Well, he's famous for his many scientific theories, most famous for his laws of motion, his work on gravity, and perhaps his work on gravity is what he's best known for, and also for inventing the mathematics of calculus, which in math circles certainly is what he's most appreciated for. His most monumental publication was the Philosophiae Naturalis Principia Mathematica Principia, or Principia, was published in 1687 in his early life. Interestingly, kind of got this theorizing and this work, and became more of an administrator in his later life, including operating the Royal Mint of Great Britain, where they minted coins. A quote from him where he says, "If I have seen further, it is by standing on the shoulder of giants." So he's attempting to, I guess, be humble, right? Acknowledge that it's not like he's the only person that's come up with these ideas. He just was able to connect some dots that someone would have sooner or later, and he was in the right place at the right time. His 3 laws of motion are as follows. I just have one simple slide on each. The first law, so Newton's first law of motion, is often called the law of inertia, and it states that an object at rest or in a state of uniform motion will continue that motion unless acted upon by an outside force. Okay, so something, you can't just have spontaneous motion. Every motion or change in motion has to be explained by some force. That force can be gravity, that force can be electrical, that force can come from, pulling our world, right? Where ultimately we break down the more fundamentals of energy and so on. Every movement has to be explained by force. Things will continue to move in a straight line, that you can't move at constant speed without changing direction and not have any force to do that. That the case of that is often is, if you like throw a rock in deep space, it will continue in a straight line forever. because after you finish throwing it, there's no force acting on it. And if you are so far away from any source of gravity, then there'd be no further discontinuity. Like, in the middle of those bolts we talked about in chapter one. Another big example of inertia is riding in your car. If you come to a sudden stop, you fly forward, right? Which is why we have seatbelts or, in extreme cases, airbags, because your body has inertia. Inertia is a quantity, it's actually just your mass. And because of that, the law of inertia applies, and you need a force to stop moving at the same speed. The car, how did it stop moving? Well, because of the contact force between the tires and the pavement, but you don't have a direct connection to that force. So what's going to happen? You need something else to stop you, like the support force of the. That's it for the first law of motion. This one's called the law of acceleration, and that's known by its simple formula F equals ma. Well, what does F equal ma tell us? Well, first
I'm
of all,
sorry,
the very.
Professor. Your audio is just a little bit glitchy. Like I
Oh,
could
okay.
only make out like maybe like half of your sentence or like a third of it.
On that. Okay. Okay.
So sorry.
No, no, yeah. It's okay. Is it better now?
Yes, it is better actually.
Yeah, that's really
Thank you.
I wonder what was happening. That hadn't happened on previous days.
It's good now. Thank you so much.
Yeah, huh. I'm really sorry about that. It must have been hard to understand me. Okay, so I will just continue on. The second law of motion, F equals ma. F is force, m is mass measured in kilograms, a is acceleration. Acceleration is meters per second squared. It's just how fast something is speeding up or slowing down. So it's the rate of change of velocity. And the statement of the law says that the acceleration of a body is proportional. Now, that's that term that we saw when we were talking about Kepler's third law, remember? And in the same direction as the net force acting upon it and inversely proportional to the mass of the object. Kind of a long sentence there. What does it mean? Well, it means that if you solve for acceleration, so if I was to rewrite this equation and write it and solve for acceleration, then I would have to divide both sides by m, and I would have F over m. So A acceleration equals F force divided by m mass. So if I want to have a particular acceleration, if I want to speed something up, then if I want the acceleration to be greater, well, then I can have a greater force. So that's what we mean when we say it's proportional. As F goes up, so does A. But this statement, inversely proportional, well, that tells us that if I have a bigger object, and by bigger I mean more massive, but I push with the same force, I'm going to get a small acceleration compared to if I have a low mass object. So there's an inverse proportionality between mass and acceleration. As mass goes up, acceleration goes down. So we would say mass goes up, acceleration goes down. So that's the relationship between mass and acceleration. Of course, you could compensate for a greater mass by just applying a greater force, but if the forces remain constant or equal, then you would get a smaller acceleration for a bigger mass. All right. And this idea between the inverse proportionality between mass and acceleration could be illustrated by pushing a small car, right? So a pushing force on a small car, you can get a noticeable increase in its speed and you can move it versus a large truck where you would get almost no noticeable acceleration. And the third and final law of Newton's three laws of motion is the action-reaction law. This is the law that tells us that for every action, there's an equal and opposite reaction. Now, what our actions and actions and reactions represent here are not some abstract idea like if I, do something bad to someone, then they're going to do something bad to me. Rather, we're talking about forces. So it's an action force and an equal and opposite reaction force. So as an equation, we could write this as F AB, so that's the force by A on B, equals the negative, where the negative tells us that the reaction is in the opposite direction, and that would be of B on A. So these are two objects that are pushing on each other. A pushes on B and B pushes back. Right? So A pushes with a force, and then B pushes with that same force the opposite way. Anytime two things crash together, they exert equal and opposite forces. Any interaction between two objects. We often think that the bigger object exerts a bigger force, and that's because the bigger object experiences a smaller acceleration, and the smaller object in a contact between action reactions, having less mass, and according to Newton's second law, would experience a greater acceleration. So the two equal forces do not result in equal accelerations if the masses differ. If like you have a small m of one of them and a big M for the other. Well, the more massive object will accelerate less, even though the forces are equal. All right, so that's it. Important to remember because it's quite easy to find yourself thinking that the bigger object exerts a bigger force, but it does not. The forces are equal. Launching a rocket is given as an example of action reaction because in the case of a rocket, you have the hot gas coming out of the back, and that is being accelerated in one direction. You push on the gas to push it out of the nozzle of the back of the rocket. Well, that push on the gas has to have an equal and opposite push on the rocket. So that's how a rocket is able to use exhaust and a valve in order to move itself. Obviously, when we walk, that would be another example. You push on the ground pushes back. That allows you to propel yourself forward. Any quick questions on Newton's three laws of motion before we move on? Oh, yeah. I see. I just saw the 14 messages about the glitching. I wish I caught it sooner. I'm glad someone finally spoke up. Thank you. Thank you. It was like my headphones just didn't have a good connection. There was some sort of like weird feedback. Yeah. I don't know why that happens most of the time, or it happens so rarely, right? Most of the time they're pretty reliable. All right. So let's carry on. So that's it for Newton's three laws of motion. What else did Newton do? I mentioned gravity. Okay. So this next law, sometimes called Newton's first law, called Newton's law of universal gravitation, but also often referred to without his name in the title, just called the universal law of gravitation, is a crucial formula for us because it talks about gravity and it's going to help us understand orbits even better. It's going to help us understand how it is that the moon orbits Earth and how it is that Earth orbits the sun. Because although Kepler's laws were very powerful in terms of these discovered relationships, between the velocity of a planet and its distance from the sun, or the relationship between the period of an orbit and the semi-major axis of that orbit. The p squared is proportional to a cubed, right? So wonderful predictive laws. But they didn't tell us much about the why. Why are these orbits happening? What is the underlying mechanism or explanation? And that's what the universal law of gravity is going to explain. So gravity fundamentally causes attraction between objects. So the way to think about gravity, what's the big picture, is that It's this fundamental force in the universe that tells us that all mass, everything that has mass, is attracted to other things that have mass. So, the moon is attracted to Earth. There's a gravitational pull, an attractive pull between the Earth and the moon. And do note that those forces have to be the same. The gravitational pull on the Earth by the moon is equal to the gravitational pull, from Earth on the moon. But yet we don't talk about us orbiting the moon. Well, that's because we're so much more massive. So we think of the more massive object as being orbited. In reality, they're actually both orbiting their shared center of mass. But when you have a really big object, that center is usually near the center of the really big object. That would be the case of Earth orbiting the sun, for example. There are cases where you have two nearly equal mass objects that are orbiting each other, like Pluto and its moon. And in that case, they actually orbit an empty spot that's about halfway between them. But that's getting ahead and complicating things. Let's get back to the basics. So, the universal law of gravity. What does it look like? It's an attractive force between two objects. So here we have two rocks in space, and they are gravitationally attracted to each other. The force has to be the same. Okay, they feel the same size force pulling them together. All right. That force causes motion because there's no other force to cancel it out if this is all there is in some empty bit of space, so then they will accelerate towards each other. If they have the same mass, they would accelerate at the same rate, according to Newton's second law. If one was more massive than the other, then one would pick up speed more slowly than the other. But they would both experience the same force, not necessarily the same acceleration, unless their masses are equal, but they would move towards each other. And we'll see that as they get closer to each other, the force would increase because gravitational force is dependent on distance. And as distance decreases, the force increases. So the closer you are, the greater the force. So this is not shown too clearly in the animation in the slides, but the arrows would get bigger as they get closer. So here it is. This is the equation that we care about. Not literally not the only one, right? But this one certainly is a very important equation for for so much of astronomy. It can apply to, everything from galaxies, stars, planets, moons, small asteroids, and so on. And it defines the strength of the gravitational force. So this is the force over here. Force is measured in a unit called Newton, right? Appropriately named after Newton. And it's equal to the product of two masses, m1 and m2, like the two rocks that we saw on the previous slide, and divided by the square of the distance between them. So r would be the distance between the two objects, and notice that it's being squared, right? So that value r squared is in the denominator. And then there's this big G out in front. And the big G is a constant. It is a constant that's called a proportionality constant. And the reason it's called that is because it allows us to write this equation as an equation. If it wasn't for big G, we wouldn't have an equal sign here. We'd have that weird little sign that, looks like a unfinished infinity symbol, right? So the proportionality symbol. But we don't need that. We can actually have an equal sign because of big G. It's an experimentally measured value that scientists have found applies to, how strong the gravitational force is. So it's like the calibration of the gravitational force. Like all of physics, it applies universally. So it can, be used to find the gravitational tug between objects here on the surface of the Earth, which is usually not noticeable, but some clever experiments can be devised to actually show two objects being pulled towards each other. But it can, obviously apply to, the relationship between, like I said, the moon and Earth, Earth and the sun, and so on. But it also has to apply and does apply to the gravitational force between two galaxies. As two galaxies are pulled towards each other, it would be the same constant. You just have to use the mass that applies to a galaxy, which would be a really big mass. And this is the value. So this value right here is a fundamental constant of the universe. It There's only a few fundamental constants of the universe. Physics seeks and has largely successfully sought to, boil down the physical world to just a few constants. I'm not saying we know where they come from necessarily. Why is big G equal to this? That's an open question. But something about the Big Bang, about the nature of the cosmos themselves, set this value. Maybe there are other universes out there that have different values of G, but this entire universe over the last 13.8 billion years has worked with this value of gravity. Okay. Now, is this G itself gravity? No, it's just the constant that tells us how strong gravity is. It's got some pretty strange looking units if you look at it, newtons, meters squared over kilograms squared. Think of those as the units that it needs to have in order to make the equation work. In other words, don't feel overly burdened by like why is it those units? Okay. It's just those are the ones that make it so that this equation holds, that we have newtons on the left side and we also have newtons on the right side, because that's necessary for this to be a true equation. The thing that's more important is I'm sure you can memorize it that it's 6.67. Those are the three numbers I remember, but I don't really think that's necessary to memorize it unless you want to show off that you remember what the gravitational constant is. But what you should take note of and remember in general is its power. Because notice it's written in scientific notation. It's a really small number. Okay? That you don't need to remember exactly how small it is, but it is necessary as a key concept that should, come easily to mind, is that the gravitational constant is a really small value. 10 to the negative 11. I mean, that's a lot of, moving into the zero place really far. Because remember, negative exponents tell us we're moving the decimal place to the left, right? So we take that decimal place and we move it 11 times until we'd have 10 zeros in front of the six and behind the one, right? Well, the one's place. So this is a very, very small number. That tells us that you need a lot of mass for gravity to be a noticeable force. Compared to other forces that are created by like chemical reactions, largely driven by electricity and magnetism, you don't need much in order to get noticeable forces. So, like the chemistry behind biology, you can get large forces from small amounts of, matter. But gravity is only noticeable with really large amounts of matter. The interesting thing is that that's the way the universe works, is you end up with these big, clumps of matter, planets, stars, and so on. And that's when gravity becomes noticeable. All right, let's look at Earth and the Sun. So Earth is denoted as M2. Often, we use M2 as the smaller one, but you don't have to. And then M1 represents the sun. Sometimes you'll see other subscripts, like actually, we could call this M Sun and M Earth, but 1 and 2 work fine as well. And there's the distance between them. So R, probably, you think radius, and it's appropriate to think radius because often we are talking about the gravitational pull between two objects that are, in orbit, or at least one of them is in orbit. And so there often is a radius involved, although strictly speaking, it's more likely to be a semi-major axis. But then again, most orbits, at least, in our own solar system, are so nearly circular that we can ignore their elliptical nature and just treat them as a circle. And you will often see that. I will often give you problems like in the homework 2, which it was writing last night and is nearly ready to get published. You're gonna treat Earth's orbit is circular. And I'll give you a moon somewhere out in the orbiting a gas giant, and we'll treat it as a circular orbit. All right. So it's a totally reasonable approximation. All right. So this relationship, this definition of gravity, which I think I've conveyed strongly, but just to say it one more time, it applies to any objects with mass, not just orbiting objects. Although I said often we will see it, but that's not a limitation. This is a universal law. All right. And all right, so and then we're going to carry on to our next slide. I have a quick question from a student that was sent to me directly that I want to answer for everybody, and that's, are we going to have a quiz? Yes. As soon as we finish with this lecture, we're going to have a quiz on lecture 3, on chapter 3. I warned you about it yesterday. Hopefully you remembered. And so, if you looking ahead would have been the best course of action, although there'll be a lot of questions about Newton's laws. There'll only be a few about, there'll be a lot of questions about Kepler's laws and only a few about Newton. All right. And it will be in just a couple minutes. We're nearly done with the slides here. If you look at the number of slides, you might think there's a lot left, but they're just a bunch of questions. And so we'll go through them, but at a good clip, and we'll be all the more prepared to answer some questions on the quiz itself after we answer some questions as a class. All right, so let me get back to it. All right, so speaking of questions, which pair of asteroids feel a larger gravitational force?
Number 1.
Okay, so number 1 with the shorter distance between them. So the left pair. Yes. And the reason is because of that square in the denominator, right? Is that what you were thinking?
Yes.
Good. And I also see that Fior and Isabel got it right. Absolutely. So it might be tempting to think that, well, maybe they're equal to each other or something, because of course in the pair on the right, you've got something that's twice the mass, but because you're not squaring any of the masses, but you are squaring the distance, changing it by a factor of 2 is going to change the force by a factor of 4. In other words, the force would be 4 times stronger if the masses were not changed for a radius of r compared to a radius of 2r. And then if you do have one of the masses get doubled, well, the case on the left is still twice the gravitational force. Okay? So if the astronaut is right in the middle between two equal mass asteroids, which direction does she feel gravity pulling her? Right smack in the middle between two equal mass rocks in space, asteroids. So your options are 1, which is to the left, 2, which is to the right, neither direction, or you give up.
Number 3.
Yep, because they cancel. That's absolutely right. Seems like just everybody got it. Nice. Yep. So we would say that the net force is 0. Net just means total or sum. So so we can see the two forces would cancel out. Should get pulled to the left and then pulled to the right, and therefore not pulled at all. Right. Okay. I'd mentioned this a couple times, but this is a good reference here. Proportionalities, the symbol means proportional to. So it does not mean that they are equal, but that they change values in the same way. So sometimes we want to talk about a proportionality because we don't care about the constants. We just want to talk about the trend, the overall behavior. So for example, distance defined as speed times time. If two cars drive the same speed, or two cars are driving the same speed. If car A drives 4 times the amount of time as car B, how much further does it travel? Well, I'll just show us the answer here. It's going to travel twice as far. Let's see. Yep. Did I say 4 times the amount? That's weird. It says twice the amount. Maybe I just remember. Yeah, I could have sworn I said 4 times. Anyway, so a car drives twice the amount of time, right? So then this would be a direct proportionality. If you double the time, you double the distance. Direct proportionality. Right. Doubles 2, travel 1/3 as long. Yeah. So we could say distance is proportional to time. Right? And distance is also proportional to speed. So you can take an equation with constants like the gravitational constant, which I was, saying is such a cool thing. It's this, universal constant. But sometimes you don't care about it. And you can just throw it out and just talk about the proportional relationship. So in that case, you could say that the gravitational force is proportional to 1 over r squared. All right, so here we are. We could say gravity is directly proportional to mass, directly proportional to the other mass, or inversely proportional to the square of distance between the two masses. That's how you would say this. So it's an inverse proportionality to the square. It's also just called an inverse square proportionality. So inverse because it's in the denominator. And as I said, as R goes up, F goes down, kind of like when we were talking about Newton's second law and the relationship between M and F. But here we have a relationship between distance and F, separation distance, R. So this is all 3 of the proportionalities that you can pull out of the equation of universal gravitation. It's just a real helpful way of kind of often like boiling down what you want to actually take away from the equation. You don't have to think about it as always this thing where you have to get out your calculator, always type in the numbers, always worry about scientific notation. No, often you can just look at it and do an approximation in your head, or just at least have an expectation about how the values are going to change, which is crucial for being able to really kind of understand what you're doing or to be able to make less mistakes. All right. I got another quick question for you. Here. So we've got our 2 cases, and how much weaker is the gravitational force on the left pair? Notice that here, there's no 2m. The m's are all the same. All right, we're being asked, how much weaker is the gravitational force on the left pair? Half is this half the force, 1/4 of the force, 1/8. What do you think? Okay, we got a vote for half. No, we have a vote for 1/4. Good. I see it now. I saw the 2 and yeah. Yep, that is correct because of the fact that it's squared. So it's 1/4 as strong. All right. We've got. I'll skip over this in the interest of time. This is looking at a proportionality between the square of the period and the cube of the semi-major axis, which of course is Kepler's third law, right? And we find out that we have a relationship where it's about 3 times as long. In this case, comparing the Martian year to the Venusian year. All right, so now the last actually new concept that we're going to see, and then we'll wrap up, and I'll plan on starting the quiz right at 11. That's my goal. I think I can hit it. So Isaac Newton combined his law of gravity with Kepler's law to complete Kepler's third law, because Kepler's third law was never an equation. And he never proposed any way to make it an equation. He didn't give the constants. Okay, so here we have a the orbit, right? And thinking about the time to complete an orbit and its relationship to the, you know, the semi-major axis of that orbit. So if you take the combined mass of the mass at the center and the orbiting mass, and you multiply the square of the period, then you can get an equation where you can actually account for the values. Okay, so you can turn this into more of an equation, but it's not perfect. It's just an improvement this way. All right. So written this way, you can have if the mass of the orbiting body is significantly smaller than the mass of the center. So think of the mass of the center as being the sun, and the mass with the subscript O. So the mass of the orbiting body being Earth. Well, you can cancel out the mass of Earth because it's 1 million times smaller than the mass of the sun. By the way, that's the difference between the mass of Earth compared to the mass of the sun, 1 million times, right? So it's insignificant. So you could just leave the mass of the sun times the period squared equals the semi-major axis cubed. All right, and definitely going to be a helpful way of, if you again stick with the same units. This way you could account for different size stars, for example. This way you can vary the mass and sort of use Kepler's third law to think about different orbiting systems. So like moons orbiting planets and so on. But really, what we want to do is we want a one-stop shop version of Kepler's third law that we can just use for any system. And that's this one right here. So this is combining the universal gravitation with Kepler's third law, we get this formula. So this can be used for any orbiting system. It's got the gravitational constant, g, that's 6.67 times 10 to the negative 11. M is just the mass of the object that's being orbited. So this assumes that you got a big object being orbited by a small object like a planet around a star. All right, so you would just use the mass of the sun in the case of orbiting the sun. 4 pi squared are just more constants. All right, pi, of course, is 3.14. 4 is just the number 4. P, I didn't use an uppercase P here, but this is the period squared, semi-major axis cubed. So this part, the A cubed and the P squared, is Kepler's third law. The new part is this whole group of constants. Now, they're not all constants in the case that they never change. Together they represent what would be called a coefficient, because M would change depending on what you're talking about. Are you talking about orbiting a planet or a star? And what star is it? How big is your star? All right. And so additional gravity problems, we've got time for 1 or 2. All right, so compared to the pair of asteroids on the left, the pair on the right have a force that is how much larger? We got 2 cases here. Same radius, but the masses change.
Is it 1?
So twice as large? Yeah. Yep. The pair on the right is twice as large. Nice. Because 4m is twice as big as 2m. Very good. Okay. This one. Oh, this one's interesting. So, okay. So Alexander, Fiorenina, yep. I've gotten 3 votes for 2. So everyone's saying that's 3 times as large. So looking at, it's because I think that there's the product of the masses. So it'd be 2m times 2m. And over here, this is going to be 3 times 4. So here the product is 12 on the right, and then the product is 4 on the left. So yep, sure enough, 3 times bigger. 12 is 3 times bigger than 4. Okay, basically already did that one. All right, and last one. Planets Miranda and Arrakis orbit in circles around their sun. If Miranda is 6 times as massive as Arrakis, How does the gravitational force on Miranda compare to Arrakis? Okay. One. I think one is right. Okay. Yep. Because it's just the direct mass relationship. Six times the size of the planet, six times the gravitational pull from the star that you orbit. All right. You all seem to have this down. You'll ace that part of the quiz. All right. So with all that in mind, let me stop our recording. We're now done with chapter 3.